All right, welcome back for another exciting lesson. We're at 2.3, analyzing rational functions. In 2.2, you went through, you looked at graphing them. Now we're going to say, what did you learn in that 2.2? Bring all your connections together. So first one, getting started. What are your equations of the asymptotes and the domain and the range? The equations of the asymptote have to be an equation. Do not just give a number. That would be something like x equals or y equals. So the first one, let's go here. We've got, do the easy one first. Right there you have a vertical asymptote. So that vertical asymptote is at x equals 2. We're going to do the domain right with that right now. So the vertical asymptote is going to go with the domain. The domain is what we can't have. It is x where x cannot equal 2. But it can equal anything other than that 2. We can find that value of 2 by looking at the graph and looking at the denominator. The NPVs, the non-permissible values, the restrictions on that denominator, give us our vertical asymptote. So your x minus 2, we can't divide by 0, so we're saying for the domain that it cannot equal 0. So x cannot equal 2. That gave us the restriction on the domain. If we're looking at the asymptote is the place where the domain cannot be. Where the graph is not, that's where the asymptote will be. So if x cannot equal negative 2, x equals 2 is the equation of the asymptote. They are completely related there. Let's go to the next one. Let's go to horizontal now. So horizontal asymptote, if we look at this one, goes through that line. That line that we have there is y is equal to 3. If we look at the range goes right hand in hand with the horizontal asymptote. It's y where y cannot equal 3, but y can be anything else. So it's an element of those reals. We're going to look at how to find that number there. And it's nice to see if you can make a connection with that number 3 and that equation of the graph. Making sure you always read your instructions. You need your windows here. What those windows do is it's actually a decimal window, a zoom decimal, and you're looking deeper into the graph. So you need to have that. This is the way that the calculator has to be set at to see any holes in the graph. And we're going to be looking for any holes here. So let's start with this first one. Taking your NPV, which we've said is from the denominator, x cannot equal 2. We're going to look at the points getting ever so close to that 2 from either side, from the left side and from the right side. So at 1.9, if we take 1.9 and you plug it for anywhere you see an x in the equation, you're going to get 1.9 squared minus 4 over 1.9 minus 2, and it comes out with 3.9. If you put in 1.99 into the equation, you're going to get 3.99. If you put in 1.999, 3.999. Ooh, that looks like it's getting ever so close to a number. Let's start with 2.1, and I'm going to work my way backwards. At 2.1, it was 4.1. At 2.01, 4.01. And then 4.001. And you should be able to say, what is that getting ever so close to? Oh, well, they look like from either side it's getting close to a y value of 4. So we can say that x can equal 2, but when it gets close to 2, it will be close to 4. Let's look at what the graph would be. If we graph this, and jump to here, if we start graphing this one, punching it into our calculator, we're going to notice this. Starts getting ever so close to from either side, but then right in the middle, there's a break in that graph. There's a hole. That hole has a special name. It's called a point of discontinuity. But that graph is going to be at a value of 2, 4. That's what it's saying right here. The graph has a hole at the point of 2, 4. So x equals 2 is a non-permissible value. As x approaches 2 from the left or right, y approaches 4. X never reaches 2, and y can never reach 4. So there's not actually an asymptote at that point. An asymptote is a line, but there is a hole, a specialized case of asymptotes called a point of discontinuity. Okay, making one slight change. Instead of having it x squared in the numerator, just x minus 4. As soon as we do that, we've got a little bit of a, or quite a bit of a change in the shape of this graph. Doing the exact same thing, plugging in, seeing what happens here. So if we plug in 1.9, we get 21, then 201, then 2001. It does not seem to be approaching a number. It's just getting larger and larger and larger. Let's work backwards from the other side. Negative 19, negative 199, negative 1999. Again, they're not approaching the same number. They're not coming towards the same spot. They're just getting larger and larger and larger. So it looks like if we kept going closer and closer to the value 2, those are going to go closer and closer to infinity, or negative infinity. Let's see what happens, though, when we take large numbers, negative, small, see what happens here. So we start at negative 1,000. We get 1.0020. Negative 100, 1.0196. 1.0385. 50 is 0.9583, 0.9796, and 0.9980. As we can see, from either point, as we get larger and larger, negative 1,000 or 1,000, they seem to be getting close to a value of 1. Interesting. Looking at what this graph is going to do when you punch into your calculator. At 2, you can see that they're going in opposite directions away from each other. But they're getting ever so close, but they're not going to touch that 2. And when we get to 1,000 or negative 1,000, it's getting ever so close to, but it's not crossing that 1. Again, try to look at why 1. The other one was 3. Why was the other one 3 at the beginning and this one is 1? All right. Oh, there's that outhouse picture again. This is just to remind you, asymptotes are like an outhouse. You want to get ever so close, but you want to hover. You don't want to cross it. Bad things happen when you cross an asymptote. We're talking about rational functions here. Rational, fancy word for fraction. The characteristics now, they're going to be, what our goal is we want to be able to visualize what the graph is going to look like before we punch it into a calculator. So, characteristics. We're looking at the NPVs of x. Consider this function here. Since our denominator cannot be 0, we can't divide by 0, anything that's going to make that 0 is an NPV. So x cannot be 3 and x cannot be negative 1. Those are our NPV values. The domain is x cannot equal 3, x cannot equal negative 1. But the asymptotes are going to fill those spots. The asymptotes are where the restriction of the domain is. Okay, and into your bit.ly voting link here. What are the NPVs of this graph? A, B, C, or D? Pause it now, do a quick vote, and then come back in. Now, still looking with those NPVs, look at what happens here. If we have this slightly different change of our example. The denominator cannot be 0, so we still have exactly the same. We've got our NPV. X cannot equal 3. But notice that they both have a common factor of x minus 3. Ooh. We got some karate chopping to do here. Hiya, gone. We're left now just with y equals x plus 1, where x cannot equal 3. You have to look at the NPVs that were originally there still have to be the NPVs at the end. So even though this looks like a linear, hey, that's a line, but there is a restriction on that line, and you still have to take that into account. You can't forget about it. So when we graph it, we get that hole. And that hole, the special name again for that hole, is a point of discontinuity. The graph gets ever so close to that point, but never actually will touch it. It's a specialized case of the asymptote. It's not a line that it gets ever so close to. This time it's a point that we get ever so close to. So we want to be able to figure out where is that point as well. We know that the x value is 3. It's 3 comma something. And in this case, we look at it and go, oh, it's 3 comma 4. So we can see it from the graph. We want to be able to do it algebraically as well, but we won't do that right now. Now, if we look at that note there, if we look at these two equations, all that we did is we put an extra x plus 3, oh, sorry, not there, x minus 3 factor into the numerator and denominator. The graphs are going to look exactly the same. We're going to be able to cancel off one of those x minus 3's, hiya, and we get the same equation. We say, oh, but what about the hole, the break in the graph? Well, that's already been taken care of because the x minus 3 is still there. So the hole is really on top of the asymptote, and we don't have to worry about it. So we're going to have an asymptote instead of a hole there. So now, think this one further. This is an important question. If I changed it up, would this graph have a hole or would it have an asymptote? You have to decide. Try to decide before you punch into your calculator. I want you to punch it into your calculator. I want to discuss this one next class. This is an important concept on this one. And then why is it a hole or why is it an asymptote? All right. Checking your understanding here, number one. Do we have a vertical asymptote or do we have a hole? Well, we know that x cannot equal negative 5. We know that. But is it going to be a point of discontinuity, a hole, or is it going to be an asymptote? Well, the way that we figure it out is we got to factor that numerator. So then y is equal to, hey, that's a difference of squares. X squared minus 25, that goes to x plus 5, and x minus 5 over the x plus 5. Oh, there we go. Hiya. As soon as we take off that denominator, we lose the asymptote. The denominator is gone. So therefore, this is going to have a hole at x equals 5. And it's going to be 5 comma something. Sorry, negative 5. Negative 5 comma something. Let's look at the second one. Okay, is it going to have an asymptote or is it going to have a hole? Well, again, first thing, look at that denominator. X, do your NPV, x cannot equal 2. But is it an asymptote or is it a hole? Well, factor your numerator. You get 2 bracket 2x plus 1 over x minus 2. We don't have a common factor here. Because there's no common factor, we don't lose the denominator. Therefore, in this one, we have an asymptote. And that asymptote is going to be at x equals 2. Okay, on the side there for yourself, think it further. Can you answer this question yourself? If you have a parabola with a hole, what kind of equation would you have to start off with? What would cause a hole in a parabola equation? Challenge yourself. See if you can get that one. We'll discuss tomorrow. Okay. So for some of you, this next part of the lesson here may be a little bit confusing. That's okay. Make sure you go through. When I do the questions, it might click a little bit more, but that's where we'll go through and I'll help you with them. So consider this function. The degree of the expression in the numerator is less than the degree of the expression in the denominator. This is important. Numerator is less. Oh, we're talking about degree. Degree of numerator is less than degree of denominator. I'll write it as this. D of numerator is less than D of denominator. Special case here. So now, as the x value, either positive or negative x, doesn't matter. As we get larger and larger, that's what this symbol is meaning. As the absolute value of x, positive or negative x, gets closer and closer to either infinity or negative infinity, what's going to happen to the y value? Well, the y value is going to start approaching 0. The reason for that is that the negative 4 on the numerator doesn't change. But the denominator is really going to become infinity plus 4. It's going to get really to a 0. Something divided by a very large thing gets very close to 0, to nothing. Think about it. If I have $4 and I divide it up amongst a billion people, everybody's pretty much getting nothing. That's what that's saying there. What that shows us is that we therefore have that horizontal asymptote is going to be at y equals 0. All right, back to the bit.ly vote there. Which statement is true about this function? Pause it, answer your question, and then we'll discuss. Okay, so now we'll start to look at this one. Consider this function, 2x minus 3 over x minus 1. In this case, our numerator of the denominator has the same degree. Numerator and the denominator are the same. So I'm going to call it d of n equals d of d. because the degree of the numerator is equal to the degree of the denominator. If this is the case, if we start talking about the money, the numerator changes as x gets large. The denominator also changes as x gets large. But if we look at it, it says 2x in the numerator. The numerator is increasing twice as fast as the denominator. So if I start getting a large x value, let's say 1,000,000. If I put 1,000,000 into the numerator for the x in the numerator, it's going to be 2 times 1,000,000 minus 3. That's pretty darn close to 2 million. In the denominator, I would have 1,000,000 minus 1, and that's pretty darn close to 1,000,000. So I've got 2 million over 1 million. That looks like that's getting close to 2. So let's look at what happens now. If we have the degrees the same, we're going to use our synthetic division. We're going to do some dividing. So we take our 1, same way that we did synthetic division, x minus 1, so x equals 1. Work it through, drop the 2 down. Oh, look at this, remainder was negative 1. The quotient here is 2, and your remainder is negative 1. If we go and we write that, we've got a quotient plus, so remember what we did for our statement. We got our polynomial, or our dividend, equals your quotient minus your remainder over your dividend. And that's all that we've done here. The quotient was 2 for that. Now, as we look at what happens as it goes to infinity, when we plug that in there, again, 1 divided by a very large number is really going to be 0. So we're going to have 2 minus 0. Which will be then just 2. And with the example with plugging in 1,000,000 into here and 1,000,000 into there, you can see that the numerator goes up twice as fast as the denominator. So your value is going to be your asymptote at y equals 2. Might take a little bit of time for that one to sink in. We will look at some examples to help that one out. One thing I do want to draw your attention to, though, is when we divided, we came up with 2. We came up with the whole number 2. No variables left, just 2. Let's look at the next example. Now if we consider this equation, the degree of the numerator is more than the degree of the denominator. So I'll call it degree of n is greater than d of d. Again, let's use our synthetic division. Start dividing it up. Drop that down. There's our remainder. So our quotient in this case is x minus 1. It's not just the whole number. Your remainder this time is 1. So again, using our division statement, we can say that y is equal to the x minus 1 plus 1 over x plus 1. Quotient, our divisor, our remainder. Well, as we go large, as x becomes very large, either positive or negatively, what's going to happen to that fraction of 1 over x plus 1? Well, we're going to have 1 over a very large number. Again, like $1 to 1,000,000,001 people. Well, that's pretty much nothing for each one of them. So it's pretty much going to 0. So we can say then that are x minus 1 plus the 0. I'll show you where that 0 is coming from. This fraction goes to 0. So our asymptote is going to be at x equals y equals x minus 1. We have a special type of asymptote now. It's not one that we've talked about before. It's not horizontal. It's not vertical. It is at a slant called an oblique asymptote. Oblique just means not at right angles to, at a diagonal. So we have no vertical asymptote. Let me rephrase that. We have no horizontal asymptote, no horizontal asymptote. We have an area horizontally that it cannot equal, but there's no line horizontally that it gets ever so close to. But we do have this slant asymptote going through there. At an equation of y equals x minus 1. That is the equation of the asymptote. So here's 3 rules that you're going to need to know. And they all have to do with the degree. So the first one, and these are only talking about horizontal asymptotes. Your vertical asymptotes come from your NPVs. So vertical asymptotes from NPVs. Your horizontal asymptotes, though, are going to deal with the degree. So if your numerator degree of numerator, if it is less than degree of denominator, then you're always going to have y equals 0 as your asymptote. If, however, they are equal, if degree of numerator equals degree of denominator, then it's going to be talking about your leading coefficients. Whatever the leading coefficients are of your numerator and denominator, that's where it's going to be. So that will be at, that looks like an arrow more, y equals leading coefficient of numerator over leading coefficient of denominator. And then finally, in the third case, what happens when we have a degree of numerator being more than degree of denominator? There is no horizontal asymptote. No horizontal asymptote, but there is an oblique. And we have to use synthetic division to solve. Use division to solve for oblique asymptote. And it's always going to be the quotient of the division. So the quotient of the division is what you're looking at. That's pretty intense. That's pretty intense. So we need to really focus on this next slide. All right. Math jokes. If you get them, you probably don't have any friends. Okay. I is the symbol of the imaginary unit, and pi, an irrational number. I says be rational. Pi says get real. Oh yeah, that was intense there. All right. Let's look at example number 2 now. Use the equation of each function to predict whether its graph has horizontal or oblique asymptotes, and then write the equations of those. So we could go through, you could do your vertical asymptotes just by finding your NPVs. But we're going to do our horizontal now and the oblique. first of all, look at the degrees. The degree of the numerator is equal to 2. The degree of denominator is equal to 1. 2 is greater than 1. So looking at that other page there, we know that we're going to have to deal with an oblique asymptote. There's no horizontal asymptote in this one. Well, let's do our synthetic. First of all, actually, we should check and see, is there any common factors? And in this case, there's not. We can't factor it evenly like that to cancel off an x plus 2. So let's go through and synthetic division. 1, 6, negative 7, drop it down, 1, multiply, negative 2, add, 4, multiply, negative 8, add, negative 15, box that in. And we've got left with, this is saying x plus 4. Put a y in front of it, y equals. We don't need to worry about the remainder, just the quotient part. There's your oblique asymptote. Let's look at the second one. Degree of numerator, degree of denominator. Degree of numerator is equal to 1. Degree of denominator is equal to 2. 1 is less than 2. As soon as we've got that, hey, that's case number 1 there. Every single time we have a horizontal asymptote at y equals 0 each time. Third one. Determine the NPVs, and is it a whole or is it an asymptote? So our NPVs, we got to factor our denominator each time. So y equals x minus 4 over x plus 2, x minus 2. So our NPVs are at x cannot equal plus or minus 2. Well, nothing cancels off here. There's no common factors. So therefore, we have asymptotes, not poles. So we've got vertical asymptotes at x equals negative 2 and x equals 2. Or you could say x equals plus and minus 2. That would work as well. That's part 1. Part 2. Determine the equations of horizontal or oblique asymptotes. We've got to decide. We need to look at our degrees, and we know that the degree of the numerator is less than the degree of the denominator. So degree of numerator is less than degree of denominator. Therefore, we've got a horizontal asymptote at y equals 0 from those rules. And part 3, our domain now is going to be x where, well, we can't have our NPVs. X cannot equal plus or minus 2. And XER. Second one, go back through. You might want to try to do this one on your own and see if you can get it. All right, looking at it, we've got a factor first. So we need to factor our numerator and denominator this time. So we've got x plus 2, x minus 2 over x plus 3, x minus 3. We don't have anything that cancels off. Our NPVs are x cannot equal plus or minus 3. And because nothing cancels off, we don't have a whole, we have a vertical asymptote as well. That's a vertical asymptote at x equals 3 and x equal minus 3 and positive 3. Second part. Same thing. Look at your degree. We've got degree of numerator equaling degree of denominator. As soon as we have that, we're just looking at the leading coefficients. The leading coefficient in front of the numerator is 1, and the denominator is 1. So we've got our horizontal asymptote at y equals 1 over 1, or y equals 1. Part 3. And now we need to do our domain. So our domain is x where, and we just use our NPVs here. X cannot equal plus or minus 3 XER. Okay, so this in number 4 here. The graph of a rational function can be used to solve a related rational equation. The zeros of the function are the roots of the equation. There's 2 different methods to be able to solve this. Okay, so method 1 is to graph the left side as y1, the right side as y2. So then y1 would be equal to 8 over x squared plus 1. y2 would be equal to x. And now we're looking for the intersection point of these two. And it's point or points depending on the question. I'm going to use the method that they show in this book, and that's method 2. What they do is they take it and they equate to 0. So we've got 8 over x squared plus 1 minus x equals 0. At this point, we're going to graph y1 from the left side, and we're going to find where is that equation equal to 0. So we're going to find our zeros, or x-intercepts, of this one graph. So let's plug this in and see what it looks like. All right, so plug in for y1, 8 divided by bracket, always bracket numerators and denominators, x squared plus 1 in the bracket minus x. And let's graph that. And, oh, good, we see a 0 there. We're looking for that x-intercept. So let's do our second calculate. Let's find the 0 on that one and get close to it from the left side and go to the right side of that x-intercept. Let's look in between there, and ta-da! We get x equals 1.8. We don't care about the y value. We know it's going to be 0. So then the x is equal to approximately 1.8, and we've solved it. And again, it is very important to be able to explain what you're doing to really get this to sink in. You got 3 questions there. Explain those to yourself and write them down. All right, and for those of you who made it to the end here, it's like you're sitting in a movie theater and the credits are rolling, and sometimes at the end, there's something worth watching. I don't know if this is worth watching here, but anyways. So something that I've noticed in my classroom is that approximately about 5 out of every 4 of my students, they struggle with their fractions. So I thought I'd give you a fraction here to work through. I've got some European fractions for you. First one, a over c, how about x over c, and w over c. And you might say, well, why are those European fractions? Well, they're all over c's. All right, have a good one. See you guys in class.